Okay, very good. So let me start by recapitulating the main result from last lecture, and then we'll move forward with time change of Brownian motion and a maximal inequality. That will be what's coming up. So now recall first here. What we discussed last time. So we started last time with let M be a general continuous local martingale, and we consider here the case with an m-dimensional local martingale. So then, if you consider the process, say the matrix process YT, which is MT transposed minus this covariation MT, where so this is now in Rm by M. Okay, and then the entry is right here, MT IJ. That is the covariation in between MI and MJ. T. So indeed, in fact, so this matrix here, so indeed M is actually symmetric and positive definite. And indeed, so here we have in fact a random matrix. So correct me if I say something wrong, Roman, about the matrices, but here we are in the interesting situation where a matrix valued stochastic process. And then we consider the situation where M we considered the absolutely continuous case. So in this case, we have that MT. We express this as now identical from 0 to T, gamma S, and all of these are now random. So that is important. DS, where indeed gamma of T is ddt of MT, and indeed also is in Rm by M, and a symmetric positive, non-negative, it's not positive definite, it's non-negative definite, or positive semi-definite. So that is the situation. So now we write, we can then decompose, we write this matrix in terms of eigenvalue factorization. So this is a orthogonal matrix Q of omega times a diagonal matrix times this guy transposed. And indeed, that is the inverse of Q. That is the eigenvalue factorization of this kernel gamma. And then we introduced, so indeed, lambda is a diagonal matrix with, say, lambda 1, 1, lambda 2, 2, and so on and so forth on the diagonal. So with lambda I being greater or equal to 0. And in the non-full rank or the singular case, some of the lambdas may be 0. So that is actually important to take care of. That is what we, in the singular case, that is what we extended this probability space to have sort of another Brownian motion to borrow from in if this in this singular case. So now we introduced the notation here, lambda the pseudo inverse, which was lambda 1, 1 inverse and so forth, or let me lambda 1, 1 inverse for all say n lambda n inverse, and then zeros. So we only take the reciprocal of those that are non-zero. So here I could have wrote this slightly differently, but that is so these are the so here lambda I is equal to 0 for I greater than n. Okay. And then so that was the student version. Then we introduced lambda d, which let me write it in this way: diagonal of the indicator for lambda I being strictly greater than 0. So that is just has the matrix that has 1 on all these entries that are non-zero. Okay, so if this is non-zero, then it's 1 there, and so forth. So that is just to capture the elements of this diagonal matrix that are non-zero. That is just a convenient notation. So then remember that we introduced now B check is a standard m-dimensional Brownian motion on another probability triplet. And we consider no product space. So then the first step was from this continuous local martingale here to construct a Brownian motion. So now then we constructed, so then step 1. Then
sorry. So what are we doing now?
So now my objective here was from this martingale to construct a Brownian motion.
Haven't we done that last time?
Yeah, I just So I was just so I added, perhaps I overdid it, but I just wanted to recapitulate the result from last time.
Which one? We have two, sorry. So one we proved and the other we announced but haven't proved. So which one are we doing now?
We are doing the one we proved last time.
The one we proved last time, okay. Okay, I got it. Okay, and the one we haven't proved is in one dimension, and the one we have proved is in many dimensions.
Exactly, right? Yeah. So the one, this one is in m-dimensional. The one we will prove next is in 1 dimension.
Okay. I have a suggestion, but feel free not to do this. It seems like this proof of this result in m dimensions, we had to chase like 2 rabbits at the same time. So we had to work with 2 difficulties at the same time. One is to construct this Brownian motion and everything, and the other is to fight the artifacts of high dimensionality. There is the covariant structure may be degenerate in some dimensions, and that's why you have zeros, and you have to be careful in inverting it and so on. But in the end, it worked out fine. But why don't we do this in 1 dimension? Just if you like. Because we do this in 1 dimension, and many difficulties just disappear, right? Gamma is the same; it's just a derivative. But lambda is not a matrix; it's just the absolute value of gamma, I believe.
That's right.
Absolutely. Q is just a sign of gamma. And that's it.
Right.
We don't have to worry about this Q transpose Q and so forth, because they just cancel. Everything cancels. And it will be an interesting proof and more enlightening, I believe.
So let's say I agree with you, because in some sense this is just sort of matrix. This is just in the dealing with these sort of zeros, which didn't have wasn't intrinsic part of the construction, but and we won't need multidimensional for the next results that we announce in 1 dimension anyway. We probably don't need all this. Exactly. So let's say let's do that. So let's formulate. I agree with you, because in some sense this was this rotation was just
exactly.
It was not really necessary. So then we just let's formulate this in the 1-dimensional case. So here, because we consider m is equal to 1. Okay. So in fact, then we have that I can construct now B of t. That is just now the integral from 0 to t. And then that is now the indicator. So let me add an indicator that, let me call it just gamma. Gamma greater than 0. So this is the indicator of gamma greater than gamma s greater than 0 times gamma s to the minus a half dms, right? Plus, I think this should be correct now, plus now the integral from 0 to t, and here this is the indicator that gamma s is equal to 0 times db check os. So now here, let's so the claims you see that now BOT. So in some sense, yeah, I think it's a good idea because it gets very sort of it's simple and it's easy to see. So now BOT is Brownian motion.
Yeah, I see. Not sure about gamma. So gamma s is the derivative, right? Gamma s is the derivative.
Yeah. So let me complement. So show what gamma is. So here we have that now mt is now the integral from 0 to t gamma os ds. So then this is square root of gamma to the minus a half, and this should be the situation. So then we have that. So now we see that BOT is in fact FT adapted. So this is the filtration on the extended space. And continuous. Okay. And then we want to look at the quadratic equation of BT. So now, in fact, so this is actually, so here we have, now let's first look at the quadratic integration coming from this first term, the first term right here. That is now the integral from 0 to t, and then we have the indicator actually that gamma s is greater than 0. We have that twice, so that just gives the same thing back, but then we have this guy gamma s to the minus 1, because now we have this guy squared, and we have and now it becomes simple because you don't have to deal with the matrices d ms. Okay. And then in fact we have the quadratic equation associated with the second term, which is just the integral from 0 to t, and here we have gamma or the indicator function of gamma s is equal to 0, and then we have ds because we have Brownian motion. And then we have a term which I was a little bit negligent with last time, but in principle we also have the cross terms. So you have an integral from 0 to t, and then we have the indicator function on gamma s is greater than 0 times gamma s indicator on, sorry. So this goes away. So so this cannot, this gamma s is equal to 0 times the cross variation in between m and b check s. But it's clear that this last term is 0 because you have this product, and actually had here also gamma to the minus a half. So in fact, in the matrix case, it was a little bit harder to see that this term goes away, but now you see that it's clear that this term goes away. In fact, for two reasons. The cross variation actually, since this cross variation here is equal to 0. This is equal to 0 since M and B check are independent. Since B check and M are independent. Okay. But also for the reason that this coefficient right here will be 0. Okay. So now that is then we're left with two terms here. The first term, so let me write this now out. So now this integral from 0 to t, and then I have gamma s greater than 0. Now it becomes simple because gamma s I minus 1, then have gamma s ds. That is dms from this representation. So now it becomes really, really simple because I have that now.
Sorry, where did you get that? Oh, DM, because DMS.
DMS.
Okay.
Yeah, because the DMS, that is actually gamma s ds. So you see that from the quadratic, the kernel of the quadratic equation, I get exactly cancellation now with respect to this scaling factor. So then I add also plus the Brownian part. The integral from 0 to t gamma indicator function gamma s is equal to 0 ds. And in this case, we know that gamma s is greater or equal to 0. So this just indicates integral from 0 to t1 ds, using here that gamma s is greater or equal to 0, and that is equal to t. And that was exactly what we needed. So then by Levy characterization of Brownian motion, indeed B is Brownian motion. Okay. So that is nice now. So indeed what we did was this approach. We see that here it's quite simple. So we just sort of scaled the driving martingale appropriately, and then when it's deficit, we add borrow a little bit from the independent Brownian motion, and then we can construct the new Brownian motion here from these two processes. Okay. And in fact, so that was sort of you may think about this sort of as a whitening step. So you will make this now into a standard Brownian motion. So that was step one. And then sort of the main steps, the objective in some sense now was I wanted to show that we can write now any sort of continuous local martingale as a Brownian integral. So that is the second step. So step 2 is now to reconstruct or assemble now my Brownian motion, my martingale, and I write this now as the integral from 0 to t. And in fact, in this case, it should be sufficient. So I hope the minus sign should work now. So I should have just the square root of gamma s dbs. dbs. We need to check now that no, this is the claim. This is the claim. Know that the original martingale can be constructed from BS in this fashion right here. So we have so now I sort of scale back again in the assembling. So now we have this this construction of the Brownian motion right here. So now I will use this representation to show that indeed we recreate M. So now let me therefore check. Let me call this check, and then I want to show that this check is actually equal to MT itself. So now this is equal to now the integral from 0 to t square root of gamma s, and then here I have the indicator function on gamma s being positive, and then I have gamma s to the minus a half dms, and I have plus now the indicator function on gamma s is equal to 0 times d b check s. Okay, so those are the two contributing factors. So now then we have the integral from 0 to t. Indeed, let's see what this cancels. So I just have the indicator function now, gamma s greater than 0. Let's see how this works out. dms plus square root of gamma s, indicator function gamma s is equal to 0, db check of s. And okay, yes, so no, you see that this thing right here, this is now equal to 0, because either gamma s, this should, yeah, no, sorry here.
Looks good.
It looks, yeah, but this right, yeah, so here, yeah, exactly. This looks good. This is 0. This is 0. Exactly 0. This need to be 0, because we don't want to b check to affect m check. So this is 0, because either gamma is 0 or it's being killed by this term right here. Okay, so then we write this now as the integral from 0. I can write this now. I can write this as, this is just mt plus the integral from 0 to t. And here I have the indicator function on gamma s is equal to 0 dms, right? Because here I had I just sort of added and subtracted here the indicator function that gamma s is equal to 0. And then I have these two terms, and this term, the Brownian term, was equal to 0. So now let me call this thing right here m tilde t. And the final thing to show that m check is equal to mt is to show that this part is now equal to 0. So then if I look at the quadratic variation of m tilde t, that is now equal to the integral from 0 to t, and its indicator function that gamma s is equal to 0 times gamma of s ds. And again, either this guy is exactly the same expression I have right here, actually, just I don't have the square root. So this guy is equal to 0 again. So this is equal to 0. This is equal to 0 again. And that is nice, because now I have that the quadratic variation of this martingale, continuous martingale, is equal to 0. So then indeed, it means that m tilde is indistinguishable. It's continuous, so it's indistinguishable from the 0 process. That is actually from that's a consequence of the Meyer decomposition. That if we have the quadratic variation part is 0, then the martingale is 0. I'll comment on this after we prove Meyer. But that is the result. So a continuous martingale whose quadratic variation is 0, that is the 0 process. And that is, so then indeed we have that m tilde t is equal to mt is now the integral from 0 to t, and we have simply now square root of gamma s dbs. That is what we wanted to show. That was, yeah, it was much better. Now we see, the only thing is that we avoided this sort of rotation matrix, and we see how the scaling is the important thing. The scaling is the important thing. And if the process was deficient, it was sort of sections where the quadratic variation is 0. In fact, that means that the process is 0 over this interval. So now, the picture, so this is the picture. So the picture is actually, this picture you will see very clearly in the next result also. So we may have a situation where we have the quadratic variation process, may look something like this. So this is now MT. So here, in sections where the quadratic variation is flat. So let's say this is T1, this is T2. We have that the process stay frozen. The process stay frozen because the quadratic variation does not change. So then in this, so here in some sense, MT is sort of frozen. And we sort of borrow from lec8 to construct B. So it was exactly when this so it was when the quadratic equation doesn't change. That is when we add a little bit of the other of the B check. So let me go all the way back to here. It is when gamma s is 0. So it's when the quadratic equation does not change. Then we add a little bit of the other Brownian motion. So remember here that gamma s is actually now it's a random quantity. So it's a path-dependent quantity that corresponds to sections where the on this path the process is frozen. Okay, so yeah, so I think this was a better way to articulate it. Now we see that how we can construct any continuous martingale in terms of a Brownian integral by appropriate scaling, and when actually the Brownian motion is constructed either from the martingale itself when it's non-degenerate, or by borrowing from a sort of auxiliary Brownian motion when the martingale becomes degenerate. And indeed, we have that gamma s is, or gamma t of omega is measurable with respect to filtration, which we called f check t of mt last time. So that was from the notation last time. Because it's this is now gamma t is just a quadratic variation of my process. Okay, so it's determined by the information in the original process. And finally, let me just indeed now when you have this final remark here, indeed we have that the quadratic variation of mt from this representation of the Brownian is just integral from 0 to t gamma. So here we see that we have the square root of gamma then this becomes gamma s ds, which is just equal to, yeah, that is what we started out with. That was the kernel. Okay. Okay, so that was the first result from last time. So so yeah, I think thank you. I think this was a good way to recapitulate and articulate the important probabilistic aspects here.
Yeah. Thank you, Knut. One question.
Yeah.
For fractional Brownian motion, do you recall what the quadratic variation is?
Yeah. So with fractional Brownian motion, so then it has so the for fractional Brownian motion. So then with Hurst coefficient, H, then only, so here only the let's say it's further so it's only, so it's only when H is equal to half that corresponds to Brownian motion. So then then it has a finite quadratic variation. So let me be back there. So here, so if H is bigger than a half, then quadratic variation is 0 because it's smoother than Brownian motion.
Yeah. Okay, so that's my concern. So if it's smoother than the Brownian motion and the quadratic variation is 0, then how can this theorem be applied, right? Gamma, so you differentiate 0, you get a 0.
Right. Yeah.
Right. So try to apply this theorem for fractional Brownian motion. It doesn't work, right?
Right. Then that's a good question. Then it wouldn't work. That is right, because we have right, and that is so it doesn't work because fractional Brownian motion, in fact, is not a semi-martingale.
It's not a semi-martingale. I see.
Yeah. So that is
it's not a semi-martingale because it has kind of a momentum.
Right. Yeah.
For it to be smooth, it has to have a momentum. So if it was going up, then the conditional expectation will actually be positive, right?
Exactly. So there is sort of persistence. There is persistence exactly in the process. So that in some sense that is exactly why the main difference in between exactly this thing that has momentum is the main difference with respect to Brownian motion. So it means that the increments are correlated. So for H,
future is correlated with the past. It has to remember to go. Okay.
Exactly. So if H, that's exactly the point. If H is bigger than a half, then they're positively correlated. So we have momentum. So if H is less than a half, then quadratic variation is infinite.
And then it's infinite and doesn't apply either way, right? Okay.
Right, it doesn't apply. So because then
I was thinking again. I was thinking of a good example.
That's a good example, because it shows why it doesn't work. In some sense here, this becomes more complicated in some sense since it's rougher here, since they're negatively correlated, and it's actually the correlation that creates the problem.
I see. Okay. It's I'd have to look at better examples where things are martingales. For example, you write an exponential martingale or exponential martingale of a Brownian motion, then try to represent it in this theorem. That'll be fun exercise.
That's a good so maybe I'll think about
maybe actually even quadratic martingale. What about quadratic martingale, like bt square minus t? Let mt be bt square minus t. That's a quadratic martingale.
That's right.
And does it have a quadratic variation? That's a fourth power.
Right. So they still have this
it should have quadratic variation.
It should have it has quadratic variation since so now let's look at, if you look at the expected, so everything you have to do is to look at now bt squared minus t squared, right? So now that is actually the expected value of bt to the 4th power minus 2t, the expected value of bt squared plus t squared, and this is 3t squared minus 2 I'm in trouble, plus t squared, which is 2t squared.
And so, sorry, this is a silly question, but why is this quadratic variation? Why
yeah, so now let's say, because what we want is, so now we want so let me call this process now yt. So what we want to show is that the expected value of yt given fs that is equal to ys. No, sorry. Yeah,
that's fine. No, the definition of quadratic variation is not expected value of something squared, right? It could be non-deterministic. Actually, it could be random. It's only for Brownian.
Right. Yeah. So yes. Let me
something else.
Yeah. So let me. I believe that's, but still let me call this yt. So then what I want to show is I want to find okay, yeah, want to find this process, so that when we take the expected value of yt minus yt given that is ys minus this process. That's what we want to show. So now so now so then if I look at no, the expected value. No, that's not what I want to show. I want to have a square right here.
Square, yes.
Yeah. So now that is.
Oh, sorry. No, yt is already the square. I'm not sure what yt is really. Is yt the square?
Oh yeah, no, yeah. Yt was yt is not the square. This is yt squared. Yeah. So finally, this so with yt being this quantity right here, this is what we want to show. So, but we know that yt itself is a martingale. So then yt is a martingale. So we know that let me write this as or we want to show now that yt squared minus ys squared minus the increment of the quadratic variation given fs this equal to 0. Okay, so here is the increment of the process, and this is the increment of the quadratic variation. So this is the same now as the expected value of yt minus ys squared because y itself is a martingale. And then I subtract now this quantity. Since here we have that the expected value of ys given fs, that is ys squared. So now what I want to show now is that the increments of the process condition this is what I want to compute. The increment of the process condition on fs. So now first, this is what I want to compute. So first I compute now here the expected value, and this is then bt squared. Let me write it out. So I want to compute the following: yt minus ys squared conditioned on fs. Although this should be equal to 0. So this is then in view of ys. Ys is the Brownian motion squared minus t. So now what I end up here with computing is bt squared minus bs squared, and then minus t minus s and condition on fs.
Mm-hmm.
Let me see. Yeah, that is the increment of this process, and then in fact I squared the whole thing, right? I squared the whole thing. So now note that here at this point we can use the fact that the Brownian motion. Okay, so let me write this now as the. So let me write this as now the expected value of bt minus bs squared minus t minus s and the whole thing squared given fs. Okay, again I use the fact that Brownian motion is a martingale, so the increment of the square is just the square of the increment condition on fs. Okay, so now and you see that now this in some sense this was what I computed, started to compute, just that I had s was equal to 0, but now we have a general s. So then this is now I have to the whole thing is squared, so this is the expected value of bt minus bs to the 4th power minus 2 t minus s, and the expected value of bt minus bs squared and plus t minus s squared conditioned on fs, right? I square this whole thing, and now you see that now we get essentially what had happened, because now we have this thing, the 4th moment is 3 times the variance. So and the forward-looking increment is independent, so this is still 3 t minus s minus 2. Here I have t minus s, I have another t minus s there, so this t minus s squared and plus t minus s squared. So now I get in fact net of 2 t minus s, a net of 2 t minus s. Okay, and then if I go up again, this was the yes.
Just really quickly, I think the t minus s in the second and the last line and the second to last line should be squared. Just like a small.
Yes.
3 t minus s squared. Yeah, and then 2 t minus s squared is the net.
That's right, and that is to be squared also. Thank you. Yeah. I forgot the square here. So now we are at the 4th moment. So we have the square rather than t minus s itself. So that is nice, because now I have this expression right here. So now if I go back up, this is what we wanted to be 0, and I have computed this guy right here. So we want so then assembling things. So then we have that if I look at from this expression right here, let me copy. No, sorry. I know that this whole thing is equal to 0. And here we computed this was the expected value of ys yt minus ys squared conditioned on fs. So this implies now that the expected value of the quadratic equation at t minus the quadratic equation at s given fs, that should be equal to this quantity. So this should be equal to now to t minus s squared. Okay, so this is this now. What can we say about this? So now, so yeah, so we need to show here that the quadratic equation should be deterministic, should be equal to this thing right here. That is the claim. So that in fact that was sufficient, because if that is the case, then we have a martingale, or we have that yt minus ys, that is 2 t minus s squared. So it must be that y, it must be then that y, the quadratic equation is this should be what it is. So now
sort of, do you think there is a function satisfying that? Like f of t minus f of s always equals 2 times t minus s squared for all t and s? I don't think so.
I don't know. That yeah,
doesn't exist.
No, that is then I'm in trouble here.
Yeah, I'm sorry, Knut. I didn't want to put it in the spot on this.
But this is a good problem. It's a good problem. So
it's a cool problem to think about.
So let's.
I don't think it's deterministic. Actually, I don't think the quadratic variation in this case is deterministic.
Right. Yeah. So
I don't think it can be, because if you let s equal to 0, then you have 2t squared. But then if you look at the increment of that, you can't have t minus s squared and then s squared and have that work out. Yeah.
No, we are in some sense of trouble here. We are in some sense of trouble. So so we'll get
like Brownian. It's like Brownian motion itself, right? Yt minus, this is what Brownian motion satisfies, right? Expected value of yt minus ys.
So we have the increment.
No, it doesn't. Sorry.
No.
No. It's something else. Sorry.
Yeah. So we have so I give it 10 more seconds, and if I don't get it, I'll move on, and then I for sure will get back to it on Monday, because it's a good example. But let me, I think I will think about it and come with a clean discussion on Monday.
Sure. Sorry.
But this
turned out to be
this is that's the way to learn, to look at problems. So we can all think about it in the weekend, and I will present on Monday.
Yeah, it's also I was asking because now we have a very cute result, right? Any martingale can be represented as integral of something with respect to the Brownian motion. Now that something is almost explicit. It's the square root of the derivative of the quadratic variation. Okay. And then of course to be able to apply this theorem, you should be able to compute the quadratic variation for simple processes. And then I was thinking, okay, let's take a very simple process, the first non-trivial process, and try to do that. And it turned out to be not so easy.
Exactly. So but that is exactly the point. So if you have that's quantity, then you sort of understand the process very well. Yeah. So we'll get there. So, but that in some sense that
but is there a general? Do you know a general method, a general kind of rule given the process to compute its quadratic variation? What is it? Is it or no such?
Yeah.
Kind of all-purpose method to do that.
Right. Well, I think this approach we tried, which I failed on, is sort of a typical thing. But we also know that if we can show that with some limit theorem that let's say that the increments of the process, if you could show that that converge to something.
Yeah, that's alternative. This is kind of a direct way, right?
That's right.
What we tried is an indirect way. In the end, you have to guess this the correct thing. But this is without guesswork. You just take the limit and you're done.
That's right. So then we sort of can start from the process and its property to identify. So one of those two should work.
Yeah. Okay.
Maybe they're all two. But we'll return. So now, but for now, let's think about another very nice result, which is so we have so we'll return on Monday, but now next I will discuss another fundamental result, which is about DDS, or I have to cheat it. Dumbies, Dubin's, Schwartz, Brownian motion. So or time change.
Also, sorry. Whose result was this that we just?
Yeah. So actually, I think the result we just had in the scalar case, that was Dub originally, Dub's original result. The vector case, I'm not sure, it may have first been in Karatza's, I'm not sure, but the original scalar result was Dub.
Dub, perfect. Yeah, thank you.
So now. And then, so this result, I think it was about from 65, and two papers, one Dambis, one was Dubin Schwartz, which was essentially showing that via or time change of a local martingale, or a continuous local martingales. And we discuss as above this in the scalar case, though there are vector versions also, but the main insight comes from the scalar case. So now, the situation is the following. So so here we let M be a continuous local martingale, and the one assumption, we assume that the limit as t goes to infinity, mt, that is equal to infinity. So the almost surely, so the quadratic variation grows without bounds. So that is, we want to, via time change, come to Brownian motion, and then we need to have be able to have infinitely large quadratic variation. So in fact, in the case that we don't have this case, in general case, we can proceed. We can deal with the situation via extending state space in a similar fashion as state space in a, the probability triplet, extending probability triplet as above. Okay. So it means that at some point the quadratic variation saturates, and then you have to borrow from another Brownian motion if you want to convert via time change this guy into Brownian motion. But this is the setup when we assume this condition right here. So then we let T of S be equal to the infimum in time, such that now the quadratic variation is actually strictly bigger than S. Okay, so and since MT grows without bounds, this time is well defined for all S. No matter how large S I have, I can find such a TS. Okay, so that is now a stopping time. Because so we'll shortly stop this. This is a stopping time. So as B as stopping time. And we let now BS be the Martingale.
Yeah, why don't we write this funny thing with infimum? Isn't quadratic variation continuous and increasing?
Yes.
Because we have a continuous local martingale, so quadratic variation probably must be continuous too.
Yeah, it is continuous, yes, yes.
Yeah, but then there is just a point, the solution to this equation, right?
Yeah.
MT, this quadratic variation equals S. There should be unique T. I'm not sure why we write this infimum. It's just the time T for which quadratic variation equals S, right? Is that true?
Yeah, that is that. Yeah, essentially that is. So there is only one special case, and actually it's the situation where I may have again a situation where it's degenerate. So it's constant.
Yeah. You're right. Yeah. It's not.
That is
okay.
So then if this is my S, then this becomes my TS.
TS is the infimum of time, so it's the smallest thing.
Smallest time, where it's actually bigger, where the quadratic equation is bigger than S.
Got it. So it's actually the largest.
Yeah.
Okay.
Yeah. So it actually becomes the largest of constant intervals. So it's
okay. Resolve that. Sorry.
That's that. So that's a good point, because that is exactly why it makes a difference to have this bigger than there. And we can still deal with this situation also. So for generality, if we had assumed that the quadratic equation was strictly increasing, then this will actually be a sort of an invertible function, and it will be simpler. No, it's just a small technical point that it may have flat regions.
Okay, thank you.
So, but that's a good point. So no, but in a case we now stop the martingale at TS, and then that constructs a process B, and indeed this is a Brownian motion. But we define now the filtration GS, that is the filtration of the original triplet stopped at TS. Okay. So we define this quantity nodes here. So this is now a filtration. So then what we want to show is that in fact now B is BS GSS greater or equal to 0 is a standard Brownian motion. And we may, to be careful, we may subtract M at 0. So it starts at 0. So that is construction, and you see that here the only thing that may from this construction that may be challenging is that here when S hits exactly this level right here, then T jumps. So we want the process to be continuous. So here T may jump exactly when you hit a flat region. The thing is that when the quadratic variation is flat, then the process is frozen. That is what saves the day. Then that is what we will show. Then also the process is not changing. So here we have we move through the process with a time such that we create the correct quadratic variation, we create a Brownian motion. Here, nothing happens. The time is the process is frozen, and then this time jumps, and then we start to accumulate noise again when the quadratic variation and the process starts to move. But we sort of need to move with the right velocity in some sense to create Brownian motion. So that is what we saw about also the we need to accumulate sort of a quadratic variation so that it scales like t.
Yeah, and we have a second part to that theorem too, right?
Yeah,
that empty. Right. Yeah, how to construct backward.
Exactly. Yeah, exactly. So we can actually go the other way also, which is important and nice. So now I can actually, this is actually very useful. So now I can construct now. Moreover, we have now that MT is the Brownian motion, and I just stop it at the quadratic variation. So that is how I can construct the process now. I move sort of through the Brownian motion at a velocity that corresponds to the scaling of the quadratic variation.
Oh, this is great.
So that is quite nice, because this is quite general now. The only in some sense the only condition was that you have a continuous local martingale, and we can understand it now in terms of the Brownian motion, the paths of the Brownian motion.
Any continuous martingale is a time-changed Brownian motion.
That's right.
And we have an exact way to change the time.
That's right.
Explicit way. Okay. So can I ask a question?
Sure. Go ahead. Yeah.
Okay. So about the last part. Yeah. This starts to look very similar to Skorokhod embedding.
Right.
So which is for one random variable. Any random variable represented as Brownian motion stopped at some time.
Exactly. Yeah.
And I'm wondering if this is a partial case of this result. If Skorokhod is a partial case of this result or not.
Right.
Because usually Martingale is kind of a more general, more broad concept than just a single random variable.
That's right. Yeah. Exactly. So now.
Can you derive Skorokhod from this?
You should. That's right. Yeah, because now we show that no, we just need to have this should actually also be true for so because we have our martingales here, and we constructed by this stopped or this Brownian motion. So and indeed MT, that is a random quantity.
Is this a stopping time with this construction?
Yeah, that's also thing. So MT is actually it is an FS stopping time.
Yeah, which is okay because the Brownian motion is BS.
That's exactly BS. So this exactly. So we stop it. That's exactly what we do. We have the Brownian motion with respect to this filtration, and we stop it at a stopping time. So that is what you do with Skorokhod embedding also. So you have somehow a stopping time that give you the right random variable in distribution. So now, but how do we? So now we have the martingale.
Right? Yeah. So the question, if I have a random variable, I give you a random variable. Let's say it's a question in distribution. Let's forget all this.
Yeah.
So I give you a random variable. Can you then, out of this random variable, construct a martingale?
Yeah.
So that this random variable is just m of 1, let's say. It doesn't matter the scaling, right?
That's right. Yeah.
At time 1, so after one day,
that's right.
The martingale in distribution exactly has exactly given distribution. So can I extrapolate?
Right. That's right. That's right. Because that's right. And then
in a continuous way, of course.
That's right. That's
right. There's a trivial way, just 0 and
So and then you should it's just a quadratic variation of this martingale at time 1 that gives you the stopping time.
Exactly.
Yeah.
So the only question is this extrapolation.
Right. And so the question so given x now in L2, so we have can we find so so then so now let mt be equal to the expected value of x given ft.
Yeah.
So then so what is my filtration now?
And you need to make it continuous paths too.
That's right.
So somehow we have to ensure that this is continuous, absolutely, almost surely. Right.
So now if we can do that, so then so x must be measurable with respect to f1. If we can do that, right. So now somehow, in fact, if you somehow
and I agree, this is the only construction, right? If something works, and this must work, right? This must be
the way. So if you can think about sort of an basis of L2, so we build up this random variable, then we should be able to create a martingale that is continuous.
And this is only what you wrote. This formula only covers the past from 0 up to x, and then you have to also extrapolate into the future somehow.
Right. Yes.
You don't want x to appear at the very infinity, like in the infinite future.
That's right.
X to appear after day 1, right? So you have to cover.
That's right. Yeah. So you have to. So somehow. That's right. So now.
That's an interesting question. Huh?
Yeah. So for any the thing is, you want to let's say that in fact I think you should be able to do it.
Do it, yeah.
For any.
Into the future is actually easy, I think. Yeah. So if you can create something x, you just add a little bit of a Gaussian noise after.
That's right. Yeah.
X plus bt, for example. X plus bt, and then that'll be a marking. But how do you do this in the past? That's a problem.
Yeah. That's not entirely clear. So, but that's because I think you should be able to do it with any martingale, continuous local martingale that is not degenerate. You should be able to make such a construction. It seems.
It seems.
Yeah, but yeah. So
that's okay.
So this is also something. Let's think more about this. But this is a good construction. So we have something to chew on this weekend because I want to get this. We have two good problems. So here we have a constructing in law the variable x via this construction to make an explicit connection to code embedding.
Thank you, Knut. Thank you so much.
Yeah, sure.
Sorry about the time.
Yeah, yeah. So let me. So that is question for Monday. So we have the result, and let's prove it, and then we'll also look at a couple of examples, including this example right here next time. So now next on proof. So first, so consider now the situation. So let's consider the figure that we had above. So we have the quadratic equation. It may look something like this. And I have, say, S here. And this was sort of the case, special case, where you may have flat region. And then I have T, and this is my MOT. Okay, so this is essentially now the picture. So here, this is the mapping TS. So we have that now omega such that TOS is less than T, say. That should be equal to omega such that MOT, this guy right here should be bigger than S. Then TOS is less than T. So that is omega such that MOT is bigger than, sorry. Is bigger than S. Okay. And indeed, this is then in FT. So this guy is FT adapted. So this must be FT measurable. And indeed, this is clear now. And TOS is an FT stopping time. For, say, fixed S. Okay. So for fixed S, this is an omega, this is a random time, and it's an FT stopping time. Okay. But also, moreover, we may also have for fixed T, we may look at this quantity right here. This is now an omega dependent quantity, and for fixed T, we see that this must be here GS measurable, because that is the information gained by time TS. So here, so this is an GS stopping time, since TS is GS measurable. Okay. So this set is equal to this set, and that is GS measurable. When T is fixed, and I think about this as for stopping time with respect to the time S. So we sort of have either this axis as time or this axis as time. So now, as we have identified these two quantities as stopping times. So next, next on quadratic equation of this process MOTS. I want to look at, identify the quadratic variation of this process, because I want to show that it's a Brownian motion that is objective, right? So I need to show that it has the right quadratic variation. So that is sort of step 2 now. Next step, that is to show this. So first, let me first 2 lemmas that we'll be using. So I just remind you about a slightly extended, modified version of Dub's optional stopping. So if here, if MT is a uniformly integrable CAD-lag sub-martingale, then and TS 2 stopping times, then we have that indeed the expected value of M at capital T condition on the stopped filtration at capital S, that is MS almost surely. Okay, that was Dub optional stopping. It's a little bit different from what we proved. So remark, we proved the following result. That the expected value, here I should have an inequality since I have a sub-martingale. We proved that, we proved this result, the stopped case, the stopped version, Fs, what did we prove? We proved indeed that the stopped martingale is actually, so this is what we showed. Given f little s is what did we show? We showed that the stopped martingale is a martingale, so that is M of T minimum S. Okay. So here this is little s. Sorry. This little s. Sorry. So this is just a process that is the stopped martingale, and this is it by itself a martingale. But here we see that we are a little bit different in the sense that we have two stopping times right here. And this result follows with exactly the same proof, just using the proof of extended results. As in the case we showed, just using the discrete version of the uniformly integrable situation. Sorry, this was not so well explained. But here we had the additional condition that we had a sub-martingale and we had uniform integrability, and then in fact we have via martingale convergence, the martingale actually have a last element, and that is why we can use any. This result is true for any stopping time or two stopping times. So here, in some sense, I have the special case of the stopped martingale. But here I have the result for two stopping times. So that was Dub optional. I think actually it's either stopping or sampling. Okay. So that is what we will use here. So now you see that here we may think about these two as two stopping times. So then this result becomes a special case what I had. So here I have a martingale. If I have a sub-martingale, it will be like this. Yeah, this is the result. In any case, this is the result that we'll be using we are setting it. We are almost there. The proof will not be too complicated. We're using this is based on this Dupes optional sampling to show that we have the correct quadratic variation of the stop process for this quantity right here. So yeah, so since we are about to start the core of the proof, I think I will stop right here since my time is out. But it's I think this also will be going along with the previous result. This is also a very important and good result. Now we can articulate now via time change the martingale. Or we can relate it to a process that is actually a Brownian motion. And in the proof, we have now an explicit construction. We want to show two things. We want to show is that this process is continuous and that it has the quadratic variation. That is the Levy characterization of the Brownian motion. And here, in order to prove that it has the correct quadratic variation, we will use the optional sampling. So that is the path ahead. So yeah, so I'll stop right here. Thank you for questions. Any further remarks? Or so I have some homework to do this weekend. So I'll be working on those, and hopefully we'll have some good results on Monday. Okay, guys.
Thank you.
Sure. Okay. Thank you for attention. Have a good end of the week and weekend.
Thank you. You too.